Hello.
Hello, good evening, sir.
Good evening, Narendra.
Good evening.
Are you able to hear my voice?
Yeah, sir.
And screen, is it visible?
Yes, sir. Sir, is the last lecture?
Yes, Narendra. This is 12, week 12. So this
Okay.
is the last time. Uh, anyway, so I mean, uh, mm, actually we started somewhat late today. But anyway, the thing
Okay.
is, I hope I have given you some sort of better understanding of this subject through this our small interactions. Uh,
Yes,
so
sir. Okay,
uh,
I will have a comment at the end.
yeah,
Okay.
I think we should do this at the end because we are already late by
Okay, sir.
8 minutes. Priyanka is also here, so I hope
Yeah.
all the two important people are here. So we'll start. So yeah, first this recap, brief recap. First was I think Rankine cycle. So give me 1 second. I'm just opening my notes here. Yeah. So before that, I just wanted to tell you. Maybe I mentioned it last time in passing remarks regarding the Brayton cycle, which is used in a gas power plant. So So what I was trying to say at that time, actually, I should have told you this last time only, but I did not had the notes with me. So what happens with the Brayton cycle? I'll just be brief here, but you should know about this since it was briefly introduced to you. Uh, so what happens in Brayton cycle? You have seen that maximum pressure and minimum pressure. So basically, if you plot Breton cycle on TS plot, let's say, this is like actually this will be useful for our Rankine cycle discussion also, because in Rankine cycle there is phase change. In Breton cycle there is no phase change during the heat rejection process. So other than that, it's more or less same, thermodynamically speaking. So let's say we are considering Breton cycle here. Typically 1, 2, 3, 4, and I hope by this point you could identify these processes. These are constant pressure processes, and these are constant entropy. Since it is a TS plot, you can do that way. And I leave this derivation of efficiency for the Breton cycle to you in terms of pressure ratio. So if you do that, it becomes it comes out to be uh, 1 second. We'll use this symbol for pressure ratio and power gamma minus 1 by gamma. So this is a straightforward derivation. You assume air as an ideal gas, and then you can do this. Uh, but there is one more important thing that I wanted to convey here. I don't know how much time I have, but the thing is, let's say from this expression of efficiency, what you can say as pressure ratio increases, this denominator term will increase, and the whole fraction will reduce, and effectively efficiency will increase. So basically, as pressure ratio increases, efficiency increases. And by increase in pressure ratio, what do you mean? So let's say this is the maximum pressure that you can go given the material properties of that system. So that maximum temperature and maximum pressure is fixed, so you cannot go beyond certain highest pressure. So in that case, what you can do is, you know, this pressure ratio is 1 second. So there could be one more variation of this cycle. I'll use different color. What you can do is, instead of compressing it till the 0.2, you can compress it, let's say, till 0.2 dash, and this is 3 dash. You cannot go beyond P max or T max, and this will be your 4 dash. So this is the same process. It's just that you are increasing your mean temperature of heat addition. So that results in higher efficiencies that you have observed by now. But you can see, let's say you take one more, let's say one more this type of compression process. In this case, this will become your 2 prime, 3, let's say double prime, 3 double prime, and 4 double prime. So in every case, efficiency is increasing because you are increasing the mean temperature of heat addition, but area under the curve is decreasing. So that means the net heat interaction is decreasing, and by first law, this is a cyclic process, net work done also is decreasing. So in that case, there is an optimum pressure ratio that you should maintain, and if you increase the pressure ratio beyond that optimum ratio, it's of no use. So essentially, you know, like if you plot, 1 second, I'll change that to black curve. So if you plot overall efficiency of cycle versus pressure ratio and overall, net work done from the cycle with respect to pressure ratio. When pressure ratio is 1, if you put it in this efficiency formula, you'll get 0 efficiency. So this curve, if you plot, it looks like this. And again, same for pressure ratio of 1. Since there is 0 efficiency, there is 0 work done. So if you plot work done, it goes like this. So you should know that. I mean, I don't want to go into the derivation because we don't have the time. But to have maximum work output from the Breton cycle, given like maximum and minimum pressure range, there is a optimum pressure ratio at which you'll get maximum work output, but that will not give you maximum efficiency. So if you correspondingly plot it here, this will be your optimum pressure ratio, and this will be your optimum efficiency, but your maximum efficiency will be more than this, but that will give you lesser work output. So I don't have time to go into derivation of these two figures that I've shown you, and maybe they'll be not be that important for you also going forward if you're targeting undergrad level exams like GATE or anything. But if you're targeting some higher level exams like CSE, ESE, or some research related exams, there it may be useful. Then the question is, what is this optimum pressure ratio? So for that, there is a derivation, but we'll not have time to go through it. So I'll just give you the answers. So for having maximum work output, the condition is your T2 and T4 should be equal to root T1, T3, geometric mean of max and mean temperature. And if you plug that in the optimum formula for pressure ratio, which will be T2 by T1 raised to power gamma by gamma minus 1. Like you understand, right? Pressure ratio we converted into the temperature ratio using ideal gas. And now if you plug T2 as root T1 T3, so you'll get T3 by T1 power 2 minus gamma minus 1. So basically this is nothing but T max by T min power gamma by 2 gamma minus 1. I hope this is what, like, you know what this is. And by definition, like if you convert again back to the pressure, it will become P max by P min whole raised to the power 1 by 2. So your optimum pressure ratio is basically your square root of your maximum pressure ratio that can be achieved. And maximum work will be, you need to put this before work done, let's say if you put this optimum efficiency, optimum pressure ratio formula into the efficiency formula, and if you solve, then you'll get optimum efficiency as I'm not doing the whole derivation, but it is a straightforward. So I hope you can do this. It will become 1 minus root T min T max. And maximum work done at optimum efficiency, it becomes Cp root T max minus root T min whole square. This is a specific work per kg. If you have some mass, you can just multiply by mass flow rate and all. So don't focus mainly on the formulas. Those are cosmetic things. But the key takeaway from this small discussion or brief discussion is, in case of Breton cycle, or let's say Rankine cycle also, in Rankine cycle there will be a phase change. So this 1-to-4 process or 4-to-1 process, it will be a horizontal line inside the dome, the two-phase region. There also you can apply this logic, but there it will be slightly tedious derivation, and it's not important there. But for Breton cycle and all, since this optimum pressure ratio is important parameter, you should know that you never always go to the maximum pressure ratio possible. You you find a optimum pressure ratio, which is a square root of maximum pressure ratio, and there that pressure ratio will give you maximum work output. So this is about this. I should have told you last time, but I did not have the access to my notes. Anyway, so moving on, now we are going into Rankine cycle. Uh, uh, basic Rankine cycle, if you plot, I mean, Rankine cycle is basically practical power plant cycle that you see in, let's say, steam power plant, nuclear power plant, whatever. As I told you now, just now only, it is similar to Breton cycle. It's just that the pressure, like there is a phase change involved. In Breton cycle, there are no phase changes. It's a air standard cycle, so there is no phase change. But in Rankine cycle, working fluid undergoes phase a couple of times. Once in a boiler and another is in a condenser. So if you plot typical Rankine cycle, one second. It will typically look like this. And since it's a work producing cycle, you should go clockwise. These are constant pressure lines. This is a minimum, like condenser pressure. This is a boiler pressure. Let's say some another constant. So you can have 1, 2. Numbering is in your hand. That doesn't matter. So yeah, there is a heat addition here, QH. There is a heat rejection here, QL. There is a work output here, and there is a pump work here. So this is a typical Rankine cycle. There is one famous question that compare Rankine cycle with this thing, Carnot cycle. So in Carnot cycle, if you Carnot cycle within the dome, this heat addition and heat rejection processes remain same. And this 1 to 2 process, which is a turbine output process, that becomes inside the dome. That one point will be saturated vapor point, and the whole expansion will be inside the dome, and that causes turbine erosion problem because the quality of steam at the outlet of turbine is low, so there is moisture content, and which can have a turbine erosion, blade erosion problem. And this compression process 3 to 4, that also falls inside the dome for Rankine cycle, and that is difficult because it is difficult to compress two-phase mixture. With reciprocating compressor, it is not possible. You have to use some rotary compressor or some other compressors. And there also, since gas and liquid has different compressibilities, you'll have an issue of maintenance of that device. And also the condensation, the stopping of the condensation, which is 0.3, that cannot be controlled in between that phase change process. That is not in your hand. You can't control phase change because it will happen as long as you maintain constant pressure and constant temperature. I mean, any one of those quantity. So that is comparison between Rankine and Carnot cycle. This may be asked in a MCQ type of question or any interview question. That is very common question. Other than that, I think there are some ways to improve Rankine cycle efficiency. So I list down the ways. You can have a look. These are standard ways. You'll find them in any standard thermodynamics book. So ways to increase efficiency of Rankine cycle. So there are many ways. First is what you can do, if possible, reduce condenser pressure. So therefore, what happens if you reduce the condenser pressure? The heat rejection takes place at lower pressures. So this 1 to 2 process, that will be giving you higher enthalpy drop, and that is your desired work output rate. So that is one way to do it, and that's why the condensers used in steam power plant are under vacuum. If you have seen somewhere. One more advantage is the output, the quality of steam. That is disadvantage. The quality of steam coming out of turbine blades will be lower if you have low pressure, condenser pressure low. So that trade-off you have to make there. Then other thing is increase boiler pressure. But again, I mean, this increases mean temperature of heat addition. But again, when you want to increase boiler pressure, you have to heat the liquid water at higher temperatures, and that's where you need more fuel or higher quality fuel, etc., etc. So that is also cost increasing factor. So these two are quite straightforward. Then there is one thing called as superheating of steam from boiler. So when the steam is coming out of boiler, before entering into the turbine, you give a degree of superheat to that steam. So there will be no phase change during that part, but you'll have a higher work output because now your 1 point shifts to the upper part. But you have to, and one more advantage is this at the end of the expansion or at the end of the turbine work process, which is at 0.2, you'll have higher mass fraction. So the quality of steam will be higher, and that is good for your turbine blades. So that is one way. There is one more way, is by reheating. So actually these are I should ideally draw some schematics and tell you how it happens, but there is not enough time, and we have not even started problems yet, so I'll be just fast. In this case, what you do, you put, instead of one turbine, you put two turbines, and in between those two turbines, you reheat the steam coming out of one turbine and before it goes to the other turbine. So that is what it means, that by reheating the steam. So there you have two turbines, and again main what this thing turbine output increases because you are using two turbines, but then again you have to put one more turbine, so that is also cost effective, cost increasing method, but you'll have higher efficiency. These are ways to increase efficiency. Cost is another factor that is not considered here. That is one. And there is one more this thing, what is it, you do the like this third and fourth ways are for turbine related. Another is I think it is called as regeneration, and in that what you do, you take a uh, while the steam is expanding in the turbine, you take a small fraction of that steam out of the turbine before it undergoes complete expansion, and you heat the condenser water with that hot turbine steam, and then you send it to the boiler. So then the water going to the boiler is at higher temperature, and overall efficiency increases. So that you can, I think that is called as regeneration. Yeah. So uh, by regeneration you can say. So these are five ways common typically used. You can have multiple step regeneration also, like you can take steam from the turbine, bleed, it is called as bleed out. You can take at multiple points and do multiple type of regeneration thing, and that can increase your efficiency. So these are brief things to increase your efficiency. So I think that's it. One more thing is about the VCRS, uh, but I think we don't have enough time there. So we'll start with some problems for uh, you know this power plant things. Uh, First, I'll take a simple question. This will clarify your and this is a 2006 gate question for mechanical. It is a 2 mark question. It's a quite straightforward question. If if you had uh, correct understanding of the things or the cycles, you can easily solve that. So there was a table, uh, group 1, group 2, and group 3. So what is it? In group 1, let's say there are 5 choices. One is Rankine cycle, 2 is Otto, 3 is Carnot, 4 is Diesel, 5 is Breton. I'm taking this question because it covers more or less what has happened in last 2 classes for you. And in group 2, you have heat addition process. So the nature of process at which heat addition takes, and group 3 is heat rejection. So first option is, let's say A option was heat addition at constant pressure. B option was at constant volume. C option was at constant temperature. And similarly for this thing, for heat rejection, let's say I'll put another symbol. Let's say, oh my god, I'll put XYZ. So there was same constant pressure heat rejection process, constant volume heat rejection process, and constant temperature heat rejection process, and you had to match pairs. So uh, uh, like this, I found this question interesting because it covers more or less everything. Like I could have added 2 more columns also, but let's not complicate things here. So first of all, Rankine cycle. Uh, so can any one of you tell me what are the heat addition and heat rejection processes in Rankine cycle? Uh, I think uh, no one is listening. Anyway, so basically,
Hello, sir.
Constant.
yeah.
Hello.
So yeah. So I'll
Uh,
describe it this way.
the
Narendra,
ranking cycle. Heat addition at a constant pressure. Heat
Mhm.
rejection also at a constant pressure.
So it will be X. Uh, so that way you can do all other things. Priyanka, can you tell me what will be the sequence for diesel cycle, which is number 4?
For diesel cycle, heat addition is at constant pressure
Okay. And heat rejection is at?
and constant volume.
Yes. So you can do this exercise yourself also, and this was a previous year gate question. So you can understand, that this way you will remember it better. Uh, if I were in your place, I would have added 2 more columns in which work output process and work input process are also listed, and then you just do the matching. So that will give you a good idea. So this was one interesting question that I came across. Then let's go to the second. Let's go to the next question. Uh, 1 second. Let me just check. This I told you na initially this Tmax efficiency, like maximum efficiency, optimum efficiency. Uh, so that question was directly asked in 2004 GATE exam. 1 mark question directly. This formula, optimum pressure ratio formula, directly it was given in the question. So if you had known this, you could have easily gotten 1 mark. Otherwise, it would have taken a lot of time for you to solve this in exam itself. So we'll take 1 more question. This is also GATE question 2004. It is a two question common, like data question, common data question. So I'll draw a schematic of this question. That way it will be better to understand. This is a steam power plant. So there is a boiler, and let's draw it slightly bigger. The steam from the boiler is going to the turbine, which is what it is supposed to do. This is a turbine. This gives you your work output, but we are doing some sort of regeneration. So what you do is you take one bleed from the turbine, you send it back to the boiler, and this is a heat exchanger basically. So you do this way, and then finally, when at the end of the expansion process, you take out the uh, take out the steam and pass it to the condenser, and after that there will be a pump, and then it goes to the boiler. So this type of cycle is given. This schematic itself was given in the question. So I hope you are aware of all these things by now, and I'll just write the uh, the point numbers 1, 2, 3, 4, 5, and 6. So this is the thing, and it is given that steam leaves boiler at 4 megapascal and 350 degrees Celsius. So I'll give you 4 megapascal and 350 degrees Celsius. Uh, so you need this data to find out H3. So if you go to the steam table and look for the this thing, you'll get H3 as 3095 kilojoule per kg. I am actually solving this problem step by step. Uh, I understand some people don't like this way, but this is, I feel, the most time saving way to do it. Then it is given that after expansion in the turbine to 400 kilopascal, the steam is reheated to 350 degrees Celsius. So basically, it is given directly in the question itself, H4 value as 2609 kilojoule per kg, and after it is heated to the 350 degrees Celsius in the boiler, H5 is 317 kilojoule per kg, and then expanded in a low pressure turbine to 10 kilopascal. So this happens at 400 kilopascal, and H6 is given as 2165 kilojoule per kg. This is at 10 kilopascal. So condenser pressure is 10 kilopascal. You can note down that atmospheric pressure is 100 kilopascal, but inside the condenser the pressure is 10 kilopascal. So the pressure is under vacuum, and that is what we discussed initially. Like, first way to improve the efficiency of Rankine cycle was to reduce the condenser pressure, and that is what in actual practice is also done. And one more thing they have given, I think the data is incomplete here. And the question is, first you need to find efficiency of the cycle, and second it was asked that enthalpy at the pump discharge. So H2, because all other values are given, H2 is what? That is the question. So now first part should be straightforward. What is what is efficiency? It is net work upon Q Q supplied, right? So Q in I can write. Now work net is work out minus work pump and Q in. But now the question is, you don't know H2, so how will you get work of pump? So there is no easier way to do this. So I mean, what you can do if you have an access to the this thing, what do you say, steam table, but which is not in the GATE exam. So there you can't do this way. So for the time being, we can neglect the this thing, neglect pump work, and let's proceed to the problem. If you neglect this, and actually this is very low also related to the turbine work in this case. Maybe you can verify later. So if you do this, output is what is your work output? Now it is not a straightforward thing. It is this thing, regeneration type of thing is going on here. So if you want to know what is workout, it is not that easy to understand it from the this thing, this schematic. So better way is to always draw some TS or PV, anything. Here TS plot is more helpful. So what is happening is this 1 to 2 process, there is this constant pressure line. So something like this. This is your 4 megapascal line. And now what they do is, like, please ignore my bad drawing skill, but these lines should be horizontal. This is your constant pressure line. This is what your boiler is at. Then what you do is you take some this thing. You let something expand, some steam or some two-phase mixture that you don't know at this point. Let us say it is a this thing. Let me just write it down. Condenser pressure is, it's better to write this in a concise way. So this everyone knows, this is the condenser pressure. So this point will be 1, this will be 2, and out from the boiler is 3. Now the question is, where is 4? So for the timing, let's say 4 is somewhere, we don't know. We can cross check that later. But what happens between 4 to 5? It again goes to the same boiler temperature. So it goes back to this same temperature of T3. So 5 will be here, and finally it condenses like this. I mean, this should be 6. So this is what the cycle is. So now you are supplying heat at two places. One is this part, and one is during this part, 4 to 5. So, and you are getting work output. Let's say I'll put this as QH1, and this is QH2, and you are getting work output in two parts also. So net work out will be work done during 3 to 4 plus work done during 5 to 6. So and I'll put this arrow also so that there is no confusion. So this is what is happening. So now 3 to 4 is basically H3 minus H4, right? So you can write H3 minus H4 plus H5 minus H6. So you have H3, H4, H5, H6. So all these four things are here. So that is a straightforward algebra. If you do the calculation, you should get 1491 kilojoule per kg. Now the next question is, what is Q in? So that is, again, we have supplied it at two places. So Q 2 to 3 plus Q 4 to 5. Now what will be Q2 to 3? It will be H3 minus H2 plus H5 minus H4. Now the thing is, in this question H4 is directly given. So that complication has been taken care of in the given data itself. But if it was not given, then it is a slightly challenging problem, that then you have to see, then some other information should be given so that you can identify where is the point 4, whether it's a saturated liquid or saturated this thing, or two-phase mixture or something like that. Here you can look at the steam table. When the pressure is 400 kilopascal, what is the enthalpy value, what is the Hg, and if it is Hg is greater than H4, that means H4 is inside the two-phase region, and if Hg is less than H4, that means the point 4 is again in superheated region. So that way you have to check. But for this problem, H4 was given directly, so you can do the calculation directly. But now the question is, what is H2? All things are given. H3, H4, H5 are known. What is H2? That is again not given. So, but if you have solved enough problems from this topic, you by this time you should know pump work is very low and we are neglecting it. So a reasonable assumption will be H1 is nearly equal to H2. So since pump work is 0, you can assume this. So if you do that, so now it becomes H3 minus H1 plus H5 minus H4, right? Now again, what is H1? So H1 is, if you look at this thing, uh, it is a saturated liquid, and it was given in the question, I think, H1 value also. So H1 is, I think, given as 29.3. I forgot to mention here, but H1 was also given. So if you do that calculation, H1, take it as 29.3 kilojoule per kg, and if you do the calculation, you get Q in as 3626.7 kilojoule per kg, and then you get the efficiency of 41%. So now you can say that since we have neglected pump work and assumed H1 equal to H2, there the correct answer may be slightly higher or lower than this. Yeah, I understand your point, but this is what you could have done with the given data, and if you had looked at the question, the 4 options were not that close. I'll tell you, first option is 16%, second is 41%, third is 49%, and fourth is 59%. So even if you have made some assumption here for the pump work and all, this value should be fairly close to the exact answer, and you could have solved this question easily. Then there was the question was like, what is the enthalpy at pump discharge, which is H2. So for that, see, we have initially assumed H1 equal to H2, right? But now it is asked that what is the value of, like, exact value of H2. So you can make an educated guess that H2 will be slightly higher than H1, right? Because you do some sort of pump work. And if you can look at the options in the question and see, H1 is 29.3, that was given. So your H2 should be roughly in the range of 30 to 35 kilojoule per kg, or at max 40. So if you look at the option, I'll tell you the option. First one was 0.33 kilojoule per kg, second is 3 kilojoule per kg, third is 4 kilojoule, and D is 33.3 kilojoule. So just by looking at the option, you could have gotten the answer, and the exact answer is 33.3 kilojoule per kg. So this part also you could have solved easily. And if not, you know the pump work formula minus VDP. So like if you want to solve it in a subjective exam, so the magnitude I am writing, sign will be negative, that it's okay, we are just taking magnitude, and we take delta P, and this will be VF at 1, and you know this pressure is 10 kilopascal. So you can look at the steam table and you can get VF, and this delta P will be P2 minus P1, which will be P2 is 4 megapascal. So if you convert it into the kilopascal, it will be 4000 minus 10, which will be 3900 kilopascal. So that way you can find pump work also. So this is a typical problem that you will face in Rankine cycle, related to Rankine cycle. There are various versions of it, but more or less it will be similar only. There was one problem in 2008 GATE exam, again 2-mark question. So the question, like the solving of the question goes similar, because in that problem, here we are taking complete steam from 4 and giving it to the 5, and then 6, right? I mean, that part, how much of the steam you are taking out and all, that was not asked here. You have directly given H values, so you could have directly solved this. But in this 2008 question, what they did is, I'll just draw a schematic and I'll tell you how to solve such problems. I will not solve this completely because we don't have much time, but I'll just tell you how we can go about it. There was a boiler. There is a boiler, I mean. Then there is a turbine. I'm just drawing sketches here, block diagrams. Then from turbine, some part of steam is directly given to a open feed water heater, and some part, like after expansion, it goes to condenser, and some part like this is the direction of flow of this thing, and then there is a pump and it goes to the boiler again. So here it was given in the question that 20% of the steam coming from the boiler is going to the open feed water heater. So let's say if the mass flow rate of let's say from boiler, let's say m kg per second of steam was going to the turbine, 0.2 m was going to the open feed water heater, and 0.8 m was going to the like from turbine to the condenser. So this was the question. So now here also if you see 0.8 m, so at this point also the mass flow rate will be 0.8 m, and again when it mixes it becomes m, and that's how the whole thing is, mass balance is working out. So now in this question, let me do the numbering also, what was done in the question. So this was 0.1, this was 0.2, this was 0.3, and the H1 and H2 were given to you. H1 is 2800 kilojoule per kg, H2 is 200 kilojoule per kg. And this question was, I mean, you can solve this whole thing, calculate efficiency, work done, heat supplied, etc., etc. But in question, only thing that was asked is, what is H3? So, I mean, if someone doesn't read the whole question and just looks at the image and the whole paragraph of the question, they may skip the question. But in this question, the whole thing is not required at all. Only H1, H2, H3 are required. The other things are just to confuse you. And these type of questions you'll find plenty. So in this case, directly if you write, first law of energy balance for a steady state, steady flow system, assuming open feed water as your feed water heater as your system, what you can get is MH3 is equal to 0.2 m into H1 plus 0.8 m into H2, right? And directly like mm will get cancelled because that is like same on both sides. So directly H3. This is one line question. I mean, like if you read the question in hurry, you'll feel terrible. But when you solve it with a peace of mind, this is one line question. I mean, this is 2-mark question. You can imagine the way examiners try to trick people in the exam. So anyway, so this type of questions are there. Many of them are there. You can go and solve. I think I have given you enough idea about this now. Since we are at the end of the class, we'll quickly go to the VCRS, vapor compression regeneration. Vapor compression refrigeration cycle, VCRS. So VCRS, you should know there is one famous question also. VCRS, vapor compression refrigeration system, but let's say VCRS, we call it as something cycle like that. So what is there? 1 second. I want to remember there is one important thing. I mean, numericals you can solve. Yeah. So 1 second. There is very famous question in which they ask you to plot. See, everyone knows this TS plot for VCRS. This is a TS plot. Here also phase change is involved, but we don't get any work output from it because it will be very low, and the cost of putting an expander there instead of throttling valve will be not justified practically. So that's why we don't do any work. We don't expect any work output. So we just let it throttle. And this is the typical VCRS cycle on TS plot. This is a work consuming cycle, therefore anti-clockwise direction. And I hope you know this throttling process, which is 3 to 4, is not an isenthalpic process. I mean, in many places you'll find this termed as isenthalpic because H3 is equal to H4, but in reality it is not. you can just say H3 is equal to H4. You can't guarantee what is happening in between. It can be more than H3, less than H3, whatever it may be. But the only thing that you can guarantee is H3 equal to H4. So let's say in some competitive exam, if it is given that isenthalpic process is the only option, then you have to tick it. But if any interview is there, and if you say refrigeration is my favorite subject, then more or less they'll ask you about this isenthalpic process. So you should just say that it is H3 equal to H4. We don't know what happens in between. At this point, no one has told you what happens. People know what happens, but for your sake, you just say H3 equal to H4, and you cannot guarantee it will be a constant H. So that is one thing which is important. Then there is since let's say like there is one pH plot. So the reason why pH plot is used is see, if here you can see this 2 to 3 process is constant pressure, 1 to 4 is constant pressure. So rather than plotting it on y-axis of temperature, plot it on y-axis of pressure. You'll get two horizontal lines, right? So that makes your life easy. That's it, nothing else. So it is like this. The dome slightly becomes tilted here, and the process will look like this. One, two, three, four. So these things you already know. There is no new thing here. One more question that is commonly asked is why the slope of 1 to 2 line is positive on pH plot. So you have to use this TDS equation, dH minus EdP. 1 to 2 is an isentropic compression, so ds is 0. So dH is VdP. So the slope of dH minus VdP, dH is VdP. So dP by dH, which is the slope of this line, is 1 by V, which is greater than 0. So the slope is positive. So therefore it should be like this. So that is one question. And one more question that I wanted to let you know is they ask you to plot it on HS. I think that is called as Moliere, something like that. Yeah, Moliere only. But whatever it is, they expect you to plot it on HS plot. So that you should know. I'm just feeding you everything here, but 1 second. Where is it? I had that in my notes. I'm not able to find it. 1 second. It is not that frequently asked question. It is quite rare, but if anyone asks you, you should be able to answer. So it is like this. The dome will look like this on HS plot, and constant pressure lines. Let me not confuse you, because we are using dashed line for irreversible throttling process. So let me use different color here. So these are constant pressure lines. They are like this in HS plot. So these are constant pressure lines. Let's say P1, P2. And you start with point 1, which is a saturated vapor, and you compress it. So enthalpy increases. So it should actually, let me extend this line somewhat. It will be somewhat like this. So when you, let's say this is your point 1, when you compress, it goes like this. So this will be your point 2, and then you do constant pressure heat rejection, right? So you come along this pressure line, follow this pressure line, and you reach point 3, and then you do this thing, throttling. So this should be dotted line, and reach point 4, and then again 1. So it looks like this. It's a complicated drawing actually. Uh, and one more thing is you can use again thermodynamic relationships, and you can find the slope of H versus S plot at constant pressure is absolute temperature, so that is also positive. That's why these lines are positive slope. So this is how it looks on HS plot. You should work out some problems and figure out how to plot this on HS. That will be better. So that was one thing. Let me just quickly go through. Yeah, there is one more concept is there. If you remember, initially when we were studying reversible heat engines, we took 2 heat engines in series between same heat source and heat sink, and we calculated what is the overall efficiency in terms of efficiency of first engine and efficiency of second engine. In case of refrigeration, you can do the same. You can have a cascade refrigeration systems. So what you can do is, let me just draw a schematic. Cascade refrigeration system. So as the name suggests, cascading is putting 2 systems in a series. So if you just want to draw it in terms of thermodynamic sketch, so there will be one QL which you take from the lower temperature reservoir, that TL. This is your refrigerator 1, R1. Then you give some work input to it, and then it has to reject the heat, right? So let's say it is Q. Let's say it is Q. But that heat acts as a input to the refrigerator 2, which again takes some work, external work, and reject it to the QH, which is your higher temperature heat source, or whatever it is. So that these type of systems are also there, and they also exist. You can put multiple refrigerator in series, so there is no limit of 2, but we take 2 for just our ease of life. And the question is, what is like, see, this will have coefficient of performance COP, some value. This will have COP2, and the question will be what is COP overall. It is the same question which we asked for heat engines in the initial classes. Now the same question is asked in terms of COP. There it was efficiency for series of refrigerators or refrigerating systems. So I hope everyone knows the definition of COP, which is desired effect upon work input. So COP1, what is the desired effect? QL. And what is the work that you do is W1. For COP2, what is the desired effect? It is Q divided by W2. So now, if you write COP overall, what is the overall desired effect? It is again QL, right? Because that much amount of heat you want to extract. And what is the net input? This is total of these two, right? So now you have to do some manipulation to this thing. So first of all, you can see we have COP formula QL by W1, right? So what you can do, multiply and divide by W1 on both sides. So it is same, right? So this becomes QL by W1 into W1 by W1 plus W2. Just rearranging the terms, right? So this is your COP1, COP of first refrigerator. Now come to this side. What do we know? We want to introduce COP2 somewhere here. So W1 is not at all related to COP2. W2 is related. So what you can do? You can write this like W1 plus, instead of W2, you write Q by COP2. I hope everyone is on board till now. Then now what you can do is do some simplification here to this ratio term. So it will become W1 into COP of 2 divided by W1 COP of 2 plus Q. I am just doing some simplification. There is no much difficulty should be there. So we'll write whole thing together because otherwise it can cause confusion. So I hope everyone is fine by now. Then what you do, you can again do some manipulation. I hope everyone follows this thought of sequence of thoughts. And then, you know, if you apply first law to the first refrigerator, you can write Q is equal to QL plus W1 and put it here. So you'll get the numerator remains the same, COP1, COP2, COP2 plus QL plus W1 by W1, and this will be COP1, COP2, this is multiplied, COP2 plus QL by W1 is again COP1, and W1 by W1 is 1. So this is the formula for COP overall. You may not need to mug up, but you should know, because we did for like heat engines in series, so we should know for refrigerators in series. So this is the formula. One more question I think I have asked you earlier also. Question is, can COP be less than 1? I mean, if you have solved some problems related to VCRS, you would realize that COP is always greater than 1. It is about 2, 3, 4, something like that. It is not as high as 10 or something, but usually you can say 2, 2, 4, 5, 6, something like that it will be. But then the question is, can it be less than 1? So the answer is, for VCRS, COP is usually greater than 1. But for VARS, COP is usually less than 1. VA is absorption. This is not taught to you, so don't worry what this is. You may learn about this in your refrigeration course in future. But the only takeaway from this argument is COP can be less than 1. COP can be less than 1. So remember this for future exams. Yeah, then I think we are almost to the completion. I'll take one important problem, which was I felt is one of the best problem that was asked from this topic in GATE exam. This is slightly difficult problem. This was asked in 2016. I applied for GATE in 2017, but this was asked 1 year before that. And this problem many people could not solve. Because this is not a typical problem that is asked in every question related to VCRS. more or less in VCRS, you will have to find out COP, maybe heat rejected in condenser, or maybe heat absorbed in the evaporator, or mass flow rate of the refrigerant. These 4 types of problems only they'll ask. That is typical. But in case of this question, it was a slightly tedious question. I'll just draw a diagram. You'll realize what is this about. This is the last question. Okay, so please bear with me. I know we are over time, but this is, I feel this you should know. So this was given in the question, exact figure. I'm not doing any manipulation here. So this is a typical VCRS cycle. The complete compression is wet compression here. So the point 2 is saturated vapor. It is not going into superheated region. This is the direction of the process. And there is one more point which is 0. So this was given additional thing. So typically only 1, 2, 3, 4 are given in the VCRS related questions. But here 0 was given. And it is given that this temperature is 260 Kelvin, and this temperature is 310 Kelvin, and C, constant heat of liquid refrigerant, specific heat of liquid refrigerant is 4.8 kilojoule per kg Kelvin. So this is not water. Water it is 4.18, right? So this is not water, this is some other fluid. And it is given that enthalpy of phase change or evaporation is 1054 kilojoule per kg at 310 Kelvin. So at this, I mean during 2 to 3, evaporation enthalpy is given. So only this much information is given, and you need to find difference between enthalpies at state 1 and 0. So you need to find H1 minus H0. So I from whatever I have learned, like whatever problems I've seen so far, I feel this is the toughest problem, one of the toughest problem in the VCRS MCQs type of questions, like gate type of questions. So many people struggled here, and I think I would have also struggled at that point. Now I am, now it is easy for me to teach you because I know the answers. But if such problem comes in the questions in the exams, many people, this is not a typical problem that you mug up for formulas and all, no? So this is actually not a VCRS problem. This is like a combination of second law applied to the VCRS, something like that it is. But it was like when you see the question, you just remember the VCRS cycle, right? So now the way it is solved is what you do, you apply that this entropy change expression is there, right? Let's say S final minus S initial is Cp ln T final by T initial minus R ln P final by P initial, right? This we learnt in this second law of thermodynamics during that discussion, right? Now here it is a liquid refrigerant, so this term and I mean like this is for ideal gas, right, this expression. But if it is a solid or liquid, it just becomes SF minus SI C ln TF by TI. So these two things we have to use here, and those people who clicked this one, like for those people who could identify that we have to use this here, they only could have solved this problem. Otherwise, you apply everything that you have learned in VCRS, you won't be able to solve this. So going forward, I'll just complete it. So what they do is, uh, like take, this is one of the way. I mean, there is one another way, but I don't remember now, in which you do some other type of arguments. But this is I mean, this is cleaner way. Take reference temperature and entropy as let's say any T, comma S. So these are any T temperature and corresponding enthalpy. The reason is, I'll tell you. Now what you do is you apply this S3 minus ST, the second equation, which will be C ln T3 by T. So this is what you have. Then what you do? Therefore, S3 is some sort of reference entropy plus C ln T3 by T, right? Now, you know T3, which is 310 Kelvin. You know C, which is 4.8 kilojoule per kg Kelvin. But there ST and T are unknown. So, we are not getting anywhere. So, what you do? Look at the process 2 to 3. It is a evaporation process. So, we know this thing, right? During evaporation, pressure and temperature are constant, right? So, from thermodynamic relation, if you write this thing, dH equal to, sorry, TDS equal to dH minus VDP. So, for process 2 to 3, dP is 0, right? Because it's a phase change. So, you have TDS equal to dH. And again, then you integrate, temperature is constant, so this is essentially you get S2 minus S3 equal to H evaporation by T, T2 or T3, same. So now you have, 1054 was given and the temperature is 310 Kelvin, right? So now you are getting somewhere. Now you have some relationship, let's say equation 1 for S3. Now you have some another equation which relates 2 and 3. So what you do? You put 1 in 2. Then you get S2 equal to, I'm taking S3 to the other side, and then it becomes S3 equal to 4.8 ln T3 is 310 by T, and plus this term 1054 by 310. Okay, so now you have reached S2. So now, okay, we have some idea about S2, S3, but we need to find H1 minus H0, right? So we need to come to H1 somehow. So look at process 1 to 2. It is a, we have S1 equal to S2. It is a isentropic compression, right? So S1 is equal to S2. Then you can put the whole, the same expression for S1. Now, again, look at process 1 to 0. What do you see? You see similar argument which was given for equation 2 derivation for process 1 to 0. You have dP equal to 0 because it's a phase change, and again you will get S1 minus S0 equal to H1 minus H0 by T1. So now we are getting somewhere, right? Because we want H1 minus H0 and that is T1 into S1 minus S0. T1 you know, T1 is 260. Now S1 is equal to S2, but S0 is still unknown, right? So what you do? You apply this same expression, uh, the basic expression S0 minus ST will be C ln T0 by T, which will be 4.8 ln T0 will be 260 again, divided by some temperature, reference temperature. So now you have S0 as ST plus 4.8 ln 260 by T. Okay. Now you do one thing. I'll just write this as equation 3, equation 4. So now let's say this is 5. So put 4 and 5 in equation 3. So what you get? H1 minus H0 is 260. S2 is ST plus 4.8 ln 310 by T plus 1054 by 310. This is S2, complete thing. And then you are subtracting S0. So minus S0 is ST minus 4.8 ln 260 by T. So now it simplifies because ST goes away and it becomes 260 into ln 310 by T into T by 260 plus this factor, this number remains as it is. So here TT gets cancelled and now you have a numerical value. So if you do this calculation, it becomes 1103.51 kilojoule per kg. So this is your final answer. So this was a tricky question actually. I mean, there is another way in which you don't write it in this elaborate way and you just finally, because essentially what we did here is we assume some reference state and reference entropy for that temperature state, and we did the manipulation using this formula, that is for liquid SF minus SI CL TF by TI. But some people directly do that way. I find that way quite confusing. That's why I've written it in this way. So you can. I like this problem because this is like, till the time I was preparing, this was like the best problem in VCRS. I don't have much idea about recent problems. I have to look into that. But anyway, I feel you can solve the typical VCRS problems easily. But this type of problems which are quite involved, you should be aware of. So I think we'll stop here. We are already, I think, 10 minutes past our 1 hour quota. So yeah, any doubts, Narendra, Priyanka, about today's class or maybe assignments or anything?
Hello, sir.
Yes, Narendra, tell me.
Actually, I enjoyed this course of concept of the thermodynamics.
Hmm.
Exactly, I upgraded my knowledge of the thermodynamics before
Yeah,
joining this course. There was lot of misunderstanding, yeah, doubts. Obviously, this course of the thermodynamics is very complicated, very difficult, conceptual. That is a subject difficult to that is understand. Sir, you share your any experiences regarding get a competitive examination on every any topic.
Mhm.
The one thing you have given every time before taking that is a numerical say problem, you have
Mhm.
given the concept, you explain the concept, then you started the actual that is in numericals. The one thing I want to that is share, you have given the very useful that is the concept of that tapasvi in a
Mhm.
Maxwell formulation of the Maxwell any equation.
Yeah,
Otherwise, that thing was very difficult to remember, sir. Really, sir. And again, at that time also, I share that thing that throughout the thermodynamics, there are many questions on the piston and cylinder. That is an assembly, and before that, I was very doubtful, confusing regarding the understanding of that and some of the statement, yeah, problem that, yeah, process that that thing that piston is with a spring, without spring, or in a cylinder there are that is in a stuff. But you explain very suppose nicely, taking that thing suppose separately. Still I remember that piston is suppose without spring, suppose it is a moving, suppose that process is the constant pressure process. If it is with the spring, then it will follow the linear relation pressure between the pressure and volume. Or suppose there is any stops, then suppose up to the stop, then it may be the pressure will increase, so volume will remain that is any constant. So really, sir, you have given the very useful that is a concept. I really enjoyed, sir. Thank you very much, sir. I got a opportunity to learn from you also that Dev sir, Ashit Dev sir, and no doubt this is a course that Chakravarti sir, and no doubt he is an exceptional, exceptional sir. By Chakravarti sir, and you saw and in the training in this problem solving session, you have taken the different that is problems, and very that is I will say the tough problems, conceptual that is problems. So definitely by joining this course, definitely I enrich, yeah, upgrade my knowledge of the thermodynamics. Again, once more, thank you very much, sir. Not for entire that is the NPTEL thing. Okay,
yeah,
thank you, sir.
yeah. Thank you for uh, listening to my blabber for 1 hour every Tuesday, more than 1 hour.
No, sir,
So
we are really enjoyed, sir. I listen very carefully. Everything I noted in my register, sir.
yeah, so I hope that
Not only listen, sir, I record everything in a register.
yeah, that is good. Actually, through you, I hope this the reason why I chose this gate exam problems is because Abhik was already discussing assignment problems, right?
Yeah,
So
yes, sir.
there is no point in discussing same thing just in the gap of 2 days. So if I'm spending some time with students, I should bring some novelty to my talk, right? Otherwise, what's the point? So that's why I have shifted to this competitive exam, MCQs, subjective problems, etc. And I feel, uh, see, Professor Suman sir is a one of the best
Yeah,
faculty for thermodynamics. So no doubt concepts are there. He will explain everything properly. But I thought maybe I can explore this competitive exam related things, because this tapasvi thing that I told you, for me it took, I would say, almost 1.5 year to uh, come across. So it's not that easy. Such tricks.
yeah, yes, sir.
If you know, you know. If you don't, you don't. So
Yeah,
I hope through you it reaches to your students, and maybe people will be benefited. Uh,
definitely, sir.
that is one thing, and this is the last class. Maybe next semester I will take some another course also in NPTEL, but there is no way for you to know, right, which
Yeah,
TSU is doing. So
yeah,
anyway,
yeah,
it will be somewhat related to
yeah,
thermal sciences only.
yeah,
Uh, so let's hope that we can meet somewhere else.
yeah.
Uh, I mean, yeah, this is kind of an goodbye. Uh, but I also enjoyed your participation in my classes. You were from start only. I think you liked me too much.
Yeah.
Anyway, Priyanka recently she started to come regularly.
Yeah.
But yeah, nonetheless, thank you everyone to give me chance to tell you some things that I know. And yeah, happy Diwali, happy coming festivals, and let's hope that we can meet somewhere else other than this thing. Priyanka, you want to share something before we close?
So I had a doubt.
Okay. Okay, we close the session too soon. Tell me, Priyanka.
Actually, it's an old assignment, assignment 8.
Okay, 1 second. I need to open assignment 8. Okay, assignment 8. Which question?
Last question. Last question.
Last question. 1 second. It is loading.
Actually, as per the solution, they had provided, I did similar way, but the final answer, I didn't get the final answer as they mentioned in the solution.
So you are saying the numerical value is different, or what? I mean, uh, what is your question? Uh, is
Like
the numerical value not matching, or the way it is calculated is wrong, according to you?
the way they have calculated, I too did the same way, but the final answer, it differed.
So final answer here is 0.02186 kilojoule per Kelvin. What is the value that you are getting according to your calculations?
I got it as point 0.2.
Point to 10 times, huh?
Yes.
Okay.
Um.
So yeah, tell me. I have not
That
gone through this.
the last line in the solution which they have given, like with the numerical values, the first two values it was matching with what I got. The last 1.6277, I didn't get that answer.
That is Q by T ambient, right?
Q by T ambient.
So what is Q? Minus 518.55, huh? Yeah, minus 518.55, na, according to these
Yeah,
calculations.
yeah.
And what is T ambient?
It's 20 degrees Celsius.
But are you putting it in Kelvin?
Yes, 293.
So 518.55 divided by 293, right? That is 1.768. No, 1.7697. So yeah, they have given 1.6277, huh?
Yes.
Arre baapre.
So I thought maybe my maybe I did some mistake. So I asked in the forum if anyone got similar answer. No one replied.
Okay, but yeah, ambient is 20 degrees Celsius only, right?
Yes.
And now the whole system is cooled down to 30 degrees Celsius by heat transfer to the ambient at 20 degrees Celsius, and during the process, steel maintains the same temperature as ammonia. So instead of 20, if you let's say if you take 30, 500.55 divided by 30 will be 303. Then also you should get 1.711. Uh, how are they getting 1.6277? 1.6277 into uh, no, this should be divided. If 500.55 divided by 1.6277. So they are taking temperature as 318 Kelvin to get this value 1.6277. 318 Kelvin, that will be in degree Celsius 45. Narendra, have you solved this one? Any inputs? We can just look at it. cylinder of 1 kg, steel contains 0.5 kg ammonia. Both masses are 120 degrees Celsius. See, if it is just this thing, what you say? From what I can see here is there are two masses. One is ammonia, one is steel, and both of them are at 120 degrees Celsius, and finally they are at 30 degrees Celsius, and they are losing their heat to the surrounding, which is at 20 degrees Celsius. So the ninth, like you have doubt in 10th part, right? 10th question. Ninth is fine, no? Ninth question.
90 is fine. Yeah, 90 is fine.
Yeah, so if ninth is fine, then the system has lost 518.55 kilojoule of heat to the surrounding, correct? So when you do the entropy balance, what they are doing is first MS2 minus S1, that is, I assume it is for ammonia, is it not?
Yes.
So if you do this, so ammonia, its entropy decrease you found out. Then you found out for steel. Then you are founding. Then you are subtract. The minus minus will become plus. Then you are adding entropy generation due to universe. I mean entropy generation in the universe.
Sir, hello, sir. Sir, everything is correct there. Only the calculation mistake. That value is coming 1.76, but they have given in a answer 1.62.
Yeah, that's what we also usually thought.
Yeah.
So if you take 1.769,
then answer will be different.
Yeah, then answer will be almost 10 times, which is what Priyanka is getting, 0.2.
Yeah, sir.
No, my question is this the right thing? I mean, see that entropy of universe is system plus surrounding. System is steel plus ammonia. Ammonia, you are saying S2 minus S1 into mass, MS, M delta S. And for steel, you are doing CLN. It should be CLN TF by TI, right?
Yes.
So here only they have written 273 plus 30. ln 273 plus 30. What is it? There should be some another term, right? 273 plus 30. So final temperature of steel is 30 degrees Celsius. So 273 by 30 divided, 273 plus 30 divided by initial temperature in Kelvin. It should be there, right? So that is 273 plus 120. Is it not?
Yes.
So this 0.1196 value, is it correct?
Actually, that 0.1196, that answer which they got, in that they have divided it by TF.
Acha. So here they have not written, but they have taken into the account there. Huh?
Huh.
Okay, 1 second. I'll just 1 second. It is 293 divided by 120. If you add, it is 393. No. 393. 303 divided by 393, and you take log of it, and you multiply it by 0.46. Yeah. So they have taken that into account. So first two terms are okay. The last term is 1.6277. That is the only problem. See, if you ask me, it should be heat rejected to the ambient divided by the ambient temperature, because you are taking up into the like system things you are taking into account, right? In the first two terms, only this surrounding entropy change in the surroundings because of this whole heat rejection process you are considering in the end. And if you are saying this Q value is correct and ambient temperature is 293, then this 1.6277 is wrong. It should be 1.7697 something. And then you should get the point to answer. The answer that you are getting is, I think, correct. Maybe there is some typo here.
Okay.
Okay. Other than that, like conceptually, you are okay with this, right? I mean, let this typo be here because
The method is the same way, right?
yeah,
Isn't it,
yeah,
sir?
yeah. So I hope that part is clear. As long as that is clear, these things are okay. I mean, you can't do much about this.
Okay. I got doubt. I thought maybe the method is wrong or something like that.
No, 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 no. As far as I can see the ammonia in entropy interaction is first term, steel is second, and third is surrounding. So I think it's a typo. Uh,
Okay.
yeah.
Sir, and regarding the forum, they have still not answered anything.
Uh, Actually, I have raised this issue with the concerned faculty, but I don't know the like I don't have contact of the person who is responsible for uh, giving solutions as well as giving answers in the forum. So I'm sorry I cannot help you here in this regard because that is out of my scope. I only have contact of faculties who are teaching this course and no other person than this. I have raised this issue with the because one time you had suggested na initially there were many mistakes in the assignment solutions. So I have written the complete mail and send it to them, and professor has replied that he will take care of it. So I think, I mean, I don't know what else can I do in this regard.
Okay, sir. So
So
thank you very much,
yeah,
sir, for the live sessions.
yeah. I hope you understood some things that I taught here. And like I know about Narendra. What about you, Priyanka? Are you a student or are you a working professional? What is it?
Uh, I actually I'm not a student. I'm preparing for GATE exam. I completed
Uh,
my graduation.
okay, so you are planning to give this time or
Planning to give this time.
mechanical or some other?
Mechanical.
Okay. Yeah, so for you, though, this thermo part is, I think, important because I think some 10, 12 marks are there for thermo and related things, right?
Yes.
Out of 100. So it's more than 10%. So I tried to give whatever I had uh, in this limited amount of time, but I'm sure I have missed many things, uh, especially for competitive exams like GATE and all. So what I can do is I can give you my what should I do? Mobile number or email ID? I mean, this is just for being in touch. If you want, I mean, it's all up to you. So uh, I mean, I thought about it, but I then thought, okay, it's okay. Like that will be like unprofessional. Anyway, I give you a choice.
Sir,
If you
mail ID is fine, sir. Like,
so if you
in
want
case if
to,
any doubt arises, hopefully not.
yeah. So Narendra, for you also, if you have like if you want to keep in touch in future,
Yes, sir.
uh,
Give
I'll
mail ID.
mail ID you want.
Yeah.
So my mail ID is my name only, bas ulta pulta. So it is my surname Chate CHATE dot akshay@gmail.com. So this is my email ID. If you have anything, you can reach out to me. Maybe it will take some time because I have some other things here, but I'll try to answer or get back to you. Fine.
Okay.
Yeah,
Okay
thank
then.
you.
Yeah. I think
Thank
we are
you.
way
Thank you
close.
very much, sir.
Yeah. Thank you to you too also for being regular and doing things properly. And best of luck for both of you.
Okay. Thank you, sir.
Yeah. So anyway, we'll stop now. It's getting too much late now, and uh, uh, good to be in touch with you for some time, and let's hope we meet somewhere else. And yeah, that's it. So have fun and good night now.
Okay, sir. Good night to
Thank
you.
you, sir.
Yeah. Okay then. Chalo. Should I close the call?
Okay, sir.
Okay. Chalo. Bye. Yeah.
Bye.